Welcome to Homework Lib.
This is chapter 35, problem number 48. We have air, a coating, and a plastic rod. So we want in part A, we're asking for the maximum transmission. The thickness for maximum transmission onto the rod, which means, well, let's look at what's going on at the interfaces. So the inner coating interface, the incoming light is reflected, and then the phase change is going to be pi. However, since the index of refraction of coating is greater than the index of refraction of plastic rod, there is no phase change of the beam reflected from this interface. So overall phase change between these two beams is going to be pi. And we're looking for the maximum transmission, which means we want to minimize reflection, which means we're talking about destructive interference, right? So if that's the case, then the thickness is going to be m times lambda, lambda being the wavelength in air. Obviously, we have the coating, so wavelength in air divided by the coating, I'm going to call it NF, the index of refraction of the film. So if we put it here in this equation, so twice the thickness is going to be m times lambda naught over n film. So if we divide both sides by 2, then we get the thickness and lambda naught over 2nf. So if we're looking for the minimum reflection, then we have to get the minimum value for m, which is 1 times the wavelength is given to us as 510 nanometers. So I'm going to convert that to meters real fast. And then the index of refraction of the film is 1.65. From here, we find the thickness of the coating for maximum transmission to be 154.5 nanometers. Now, in part B, we're asked to calculate the thickness for minimum transmission. Minimum transmission means maximum reflection, right? So then we're looking for the constructive interference, which means twice the thickness and 1/2 times lambda naught over n film. Then we divide both sides by 2. Thickness would be m plus 1/2. Lambda naught twice the index of refraction of the film. Again, we're looking for the minimum transmission. So then minimum would be m equals 0. So then we have lambda naught over 4 times the index of refraction of the film. That equals the 510 times 10 to the power negative 9 meters divided by 4 times 1.65. Then our answer would be 77.27 nanometers.